Okay, after the constant definitions, we come into the input definitions. This is where you have whatever nomenclature that you're going to use, and you're defining that as an input. The inputs are defined as INP and a number. Now, depending on the board that you're using, this number might be different. For example, the Oak and All-in-One DC have 16 inputs on board, whereas something like the Acorn only has 8. Now, as you can see here, if you were to add additional I/O, then that I/O starts at that particular input number. This is important, especially when you're going to customize and you're adding more components to a board, because you need to figure out whether or not the board has something already defined in there, and if you're going to be use it, you need to make sure that you correctly define it to that particular input or output or whatever it needs to be. Because if not, it will not work whenever it gets compiled. Now, as you can see on here, these are also inputs, but these inputs, they have a higher input number. These right here for the 4 probe, these are actually the input numbers from the probe connector that's on the MPU11 or the All-in-One DC or the Oak board. So anything that's tied to that probe connector, it's looking for these particular inputs. And the same is true for the MPG inputs. These are all the inputs that are tied to the MPG connector on the MPU11, Oak, and All-in-One DC. Okay. Then we also have the definitions for jog pendant. And once again, that means that if you had something connected to the jog panel connector on those boards, it starts at that particular input and it gets defined in there. This is, of course, it shows that this is your row 1 or row number and your column number on that input. Now, if you were planning on using your own jog panel, you can also come in here and modify that. Or if you wanted to, let's say you're not using Centroid's jog panel, but you also have a spin over plus key or a spin auto manual key, but you have it tied to a discrete input. And if that's the case, then rather than doing this and having this set to that 1058, you set it to whatever input you're actually wiring that particular key to. Okay, and then after your inputs, we also have the feed rate override knob. And as you can see here, this feed rate override knob is an analog signal that's then being converted into a 16-bit digital value. Now, granted, as you can see, 16 bits are allocated to this, but our potentiometer that Centroid uses is only 8 bits. So that means that the other 8 bits aren't ever even used. Okay. Then after the inputs are defined, here is where you have your output definitions. Now on the All-in-One and the Oak, by default you have 9 outputs. So anything that's after 9 really isn't a physical outputs, and those outputs are in fact relayed outputs. But if you were to add, let's say you added a PLC add 1616, the first output on that PLC add 1616 starts at output 17. And of course, if you were to add another PLC add 1616, the first output on that second PLC add 1616 starts at output 33, and so on. And then of course we also have the analog output voltage that's used for the spindle. That starts at output 241, but that is also because that is on the All-in-One DC. That output does vary between different boards, so whichever board you end up using or having, you need to make sure that that is correctly set to the correct output. And of course, it is a 12-bit output. Then also coinciding with the jog panel, you have your outputs for the jog panel. The outputs are pretty much the LEDs that are being turned on and off on the jog panel. After your outputs are being defined, then of course we go into the memory bits, and they will always have the definition of mem 1 through whatever value it ends up needing to be. And as you can see here, we start off with 1, 2, 3, and then we jumped up to 11 through 15. Quite honestly, it doesn't make a difference. All it is you're just defining it to something. Chances are there was probably already other stuff that was being used on here between 4 through 10, and that stuff wasn't needed in this PLC program, so whoever wrote it just deleted it rather than going in and renumbering everything. And quite honestly, on here it goes 11, 12, 13, 14, 15. Yes, to make things simple and easy, we end up having it what goes in ascending order. But do you really need to? No. If you ended up going Mem 11, Mem 15, Mem 13, Mem 12, Mem 14, it would be perfectly fine. Now, granted, anyone trying to read it might get a little confused and it just looks kind of odd, but it's not a necessity. It doesn't have to be in a particular order. But one thing that we are doing is any kind of things like this where it's a memory bit, we do like to put an underscore, a /m, to define that that particular wording is a memory bit. It makes it very simple. Once you end up going in the logic, you'll be able to see, oh, okay, look, master enable underscore M, oh, that's a memory bit. But if I only had master enable and I'm not looking at this definitions, I'm actually looking into the logic. If I didn't have that underscore M, I wouldn't know if master enable was an input, an output, memory bit, stage, nothing. So we started adding, making sure that we add that definition or that nomenclature that easily tells us what that wording is, whether it's a memory bit, an input, output, a timer, one shot, whatever it be. So then after, keep scrolling down, now we're going into system variables. Okay, there's essentially two types of system variables. One is a system variable that the CNC software is setting, which the PLC program is looking at. The other one is a system variable that the PLC program is setting, which the CNC software looks at. These right here are ones that are going from the PLC to the CNC software. So that means that your PLC will be setting things such as do cycle start. And then the CNC software sees, hey, all right, that's associated with system variable SVPLC function 2. When it sees that, it says, okay, I need to perform a cycle start. Same thing is true for this one that says, do axis 1 plus jog. When the CNC software sees this particular system variable being set, it knows, hey, I need to do the axis 1 plus jog movement. Okay. Then we keep going down. Then we have more system variables. These are the keyboard shortcut key system variables. Keep scrolling down. These are skin events. Skin events is something that was newly added to the Centroid control. It actually allows the operator to create their own little GUI and use the Centroid software in the background. And once they use that GUI, they're essentially setting these skin events. The majority of these on here are associated with the virtual control panel that a lot of people end up seeing on there. That virtual control panel is now being used essentially as a skin, so anytime anyone hits a particular button on there, it's setting that appropriate skin event, and it tells the PLC program, hey, I hit this button, now you need to do whatever you need to do. And that is also one of the reasons why anyone that upgrades from an older CNC 11 system to a CNC 12 because they want to add that feature of the virtual control panel, well, if you don't have the PLC program appropriate for that, yes, you might see the virtual control panel on the right-hand side, but whenever you click on a button, nothing will happen. And that's solely because the PLC program hasn't been modified to be able to handle that. Okay, now back to the PLC. Alright, now we're going and we get into the system variables that are associated with custom macros. I do want to mention that there is a general misconception that people believe that whenever they create a custom macro, they're turning on that particular output that's designated by that macro. For example, people say that they create a custom macro called M10. They believe that that's going to set output 10. It'll turn it on and off depending on whether they issue an M10 or not. That is incorrect. A custom macro does not directly turn an output on or off. What it does do is it sends a bit that the PLC program looks at, and based on that bit, then the PLC program can turn an output on if it wanted to, or do other functions. But all the custom macro is going to end up doing is turning that bit on and off. And it turns that bit on and off using the M94 or M95 macro callout. Now, initially, when Centroid first started, there were only 8 bits of that M94, M95 that the Centroid control would use. And that means because of those 8 bits, certain ones were already allocated for it. For example, the M3 was already allocated for the first bit in that M94, M95 system variable. The M4 was the second bit. The flood, which is the M8, was the third. The M7 was the fifth. Now, granted, the M10 was also the fourth, and I think the M6, which is a tool change macro, was associated with the sixth bit. But reason why I'm saying this is because if you're going to create your own custom macros, now with the new Centroid software, we've got 128 of these bits. So what I tell everyone is whatever macro number you're using, just associate that particular bit with that macro. For example, let's say you're going to create a custom macro for an M13. Okay, in that custom macro, you would have a callout that would say M94/13. So on here, you would define M13 is SV underscore M94 underscore M95 underscore 13. It makes it simple. Now, once again, this M13 is just a label that's going to be used in the rest of the PLC logic. This can be labeled anything you want, but to make it easier for troubleshooting, we call it the same macro number that it's being used. So like that, when you're using things like PLC Detective, which I will go over later, when you see the M13 being highlighted, it means that the actual custom macro was being called and it set that bit. Okay? But yeah, with that, the ones that you probably don't want to change is the M3, M4, M8, and M7. These 4, you want to leave it as is because the software is actually hard-coded in there to set those particular bits. I actually do know of a customer that once tried to make things simplified, sort of like what I just did, and they issued the M3 and they tied it to the 3rd bit in that system variable macro to coincide with the macro callout. The majority of times it worked, but then there was a point where the CNC software was performing, I believe, some kind of a rigid tapping cycle, and rather than issuing the M3, it was setting bit 1 of that system variable. Well, what ended up happening when they were trying to retract, I think they busted the actual tool and they scrapped the part. So with those M3, M4, M8, and M7, please leave them just as is. But anything else that you end up creating, customizing, by all means, because now you've got 128 of them. Now, do you have to do that? No. If I wanted to, I could say M33 is associated with this system variable SV underscore M94 underscore M95 underscore 9. Okay, it just means that the 9th bit of that system variable is associated with the M33, and that means that in my custom M33 macro, I'm going to have a callout that'll say M94/9. Now, the other thing too, let's say I have a macro that turns on a bit, and then I have another macro that turns the bit off. So let's say I did go ahead and issue an M33, and inside that M33, there was just a M94/9. Okay, that means that when I issue M33, it's going to turn on the 9th bit in the system variable, and the logic in my PLC program will look at that and say, all right, that's being set. I do whatever I need to do with that. But now when I call it M34, the only thing in the M34 is just M95/9. The M95 is turning the 9th bit in that system variable. It's turning it off. So that means that now in my logic where M33 was turned on, now when I issue the M34, M33 turns off. But because the M34 was still only being associated with the 9th bit, I do not have to define the M34. I don't have to do anything like this, because right now if I issued the M34, this is incorrect, because that means that the M34 is now associated with the 10th bit in that system variable, which is not. So because I have one macro to turn it on and another macro to turn it off, but both macros are still only using that 9th bit, all I have to do is associate this with whichever one is being turned on. And if I wanted to, I do it easier to, I define it to the one that's actually turning it on. I don't have to. If I wanted to, I could call this the M34, and it just means that my logic now that is in the PLC program will most likely have to be inverted, because the M34 is when that 9th bit is turned off. But like I said, to make things simple and easier for troubleshooting, I typically assign or associate whatever I'm defining here with whatever is actually turning it on. Okay, and like I said, we will be going over custom macros later on in the tutorial. All right. After those system variables, now we come into the word definitions. The words are basically a integer value, and they are a 32-bit value. If you're going to be doing any kind of math or anything involved in that, the majority of times you're going to be setting a word value. If you're going to be using, let's say, parameters to determine what value needs to be for something in the PLC program. Perfect example for that is, let's say you have a timer. Let's say you have a machine with a tool changer, and the carousel comes in and out. But it could be a timer based, but you don't want to have a constant definition, because let's say you want to use the same program for multiple different various machines that have a tool changer. What you could do is, depending on the tool changer, the timing between how long it takes for the carousel to come in between one and the other might vary. Maybe there's a longer arm on one as opposed to the other. So rather than having a constant definition in the PLC program, and therefore you have two different PLC programs for the different machines, you can have it to where you have a parameter based, where you set a parameter based on the amount of time that you want. Well, once you have that parameter value, you need to figure out what value is in there. So you could actually have a word value associated to that parameter, sort of like these down here. It says P148 value underscore W. This right here is looking at the value of parameter 148. So then that word value would just basically be whatever value is stored in that parameter, and then the PLC program can do some math on that to figure everything else out. We will also go over that, because we will create something later on that will actually use a parameter-based value specifically for a timer. Okay. After the word definitions, we got the floating word definitions. This is also still a 32-bit, but this is actually a floating word, where the first ones were integers. This one actually has a floating word. If you don't know what a floating word is, all the floating means is that it actually has a decimal, so it deals with fraction numbers. Okay. After that, we've got our one-shots. Okay. These one-shots are essentially the things that could be needed when, let's say, you've got a momentary switch. Okay. In your logic, you can have something where when you click on a button, you want the thing to latch. All right. Even though the button itself isn't latched, it's only a momentary turn on, turn off the moment you release it, but you want that particular setting in the PLC program to be latched because you tapped it once. This is where you would use a one-shot. Now, let's say if you had a momentary, you wanted to, trying to think, for example, let's say, go back with the carousel. Maybe let's say you want to have the capability of moving the carousel yourself by pushing a jog button. All right, so you have it to where as long as you're holding the jog button, then that carousel output is turned on. At that point, you wouldn't issue a one-shot. You would just hold it on, and then the moment you let go, it'll turn off. But if you wanted, you hit it once and that carousel goes until it sees that switch, or like the carousel is in type of input, then what you would do is the moment you hit that aux key, you would set this one shot, which would latch it, and then once it's latched, then you can go ahead and use the logic in the PLC program to turn that output on. Once again, we will also go over that. We'll have examples that show exactly what one-shots and how they work. Then we come into timer base. These are essentially just timers that you might end up having in your program for various different things. The majority of things that I can think of is like if you have a fault, if you turn on an output and you need to make sure that that output sees a particular input, and if it doesn't, you want the thing to make sure that it times out, because if it doesn't time out, that output will remain on, and depending on what that output is connected to, that might cause some damage. For example, I've seen some people or some systems out there that have little solenoids that basically can't be left on. So they would have a timer that says, okay, once you turn on, look for this input, but if you don't see this input within this amount of time, turn that output off, because if not, it'll damage the solenoid. Right. Then after the timers, we define our stages. Stages are essentially groups in the PLC program. The PLC program pretty much goes through one loop every roughly 20 milliseconds. Where stages come in very handy is if there's certain things that you don't want to be turned on. For example, let's say that there's an ATC stage. Okay, a lot of times you don't want that ATC stage on all the time. You pretty much just want it whenever you're performing a tool change. So what you can do is you can have a bit that gets set that will have logic in the PLC program that says, all right, when you're going to command a tool change, now I can turn the stage on. That actually speeds up how often the PLC program goes through, because rather than constantly going through every single line, if that stage isn't turned on, it skips right past it, so it won't perform anything in the logic. That should also be, because I mentioned that, you should also be aware that if you have certain things that aren't being turned on, like certain stages that don't get turned on, have to understand that a lot of times when you're going to troubleshoot, if you have logic that should be turning outputs on, but all of a sudden you see that there's nothing happening, you'll see in the PLC detective, which once again we'll go over later on, that if that stage isn't on, even though all the conditions in that logic have been met, that output should be turning the thing on, but if that stage isn't on, the PLC program is completely bypassing it. Okay. Now there are certain stages that are required in the PLC program. First off is the initial stage. Now the initial stage is important because this is a stage that gets run the moment that the system is powered up. And by the system, I mean the software as well as the hardware. Because once you end up powering up that entire system, whatever's in that initial stage, that gets set. And a lot of times they set other various stages, set constants or timers. A lot of that stuff is handled in the initial stage. Where this is important is, let's say you customize the PLC program, you modify something in the initial stage, but you don't remember to power up the entire system. Like let's say you just exit out of the software and the hardware is still being turned on, and then you restart the CNC software. Well, when you restart the CNC software, the PLC program is not going through whatever logic is in that initial stage because the hardware never got powered up. Okay, so you have the initial stage, you have the watchdog stage, the main stage, and then of course the error stages. All these stages are important and are required in the PLC program. All these other stages that are on here, these are just add-ons that have been pretty much added on to make things a little easier. Now, the majority of times that you're going to be creating or customizing your own PLC program, you're pretty much going to be adding that logic inside the main stage. Okay. And after the stage definition, all your definitions for the PLC program have been met. Now we actually go into the actual logic of the PLC program. Okay, we have the watchdog stage, the initial stage. I will show you that you'll see that all these stages are basically have the format where they have above the actual initial stage wording, there's a semicolon with a bunch of equal signs, and then after that there's a semicolon with a bunch of equal signs. This just is an easy visual representation. So like that, anyone that's troubleshooting, they look at this and see, oh, this is a stage. Okay, it's more of a format issue, and we typically try to keep that same format. And like I said, it just makes it cleans the program up, and it just makes it easier for anyone that's going in and reading it and saying, oh, okay, this is a stage. Okay. All right. Things to mention. In your program, this is basically written in the simplest form of C code or C logic.